Alright, welcome back to my YouTube channel. Today we are going to be talking about a soft problem on perturbation theory within quantum mechanics. So we are given this problem, a matrix Hamiltonian, and we are asked to find the energy corrections for this Hamiltonian up to the second order perturbation theory. So let's then deeply. So by solution, we are first of all going to write the matrix Hamiltonian in terms of two matrices. So one is going to be the unperturbed state and the other is going to be the perturbed state. So look at this, where we have H naught to be this and H prime to be the other part. Both of them added together makes up back our Hamiltonian H. So I had to factor out a factor of 1/10 from this matrix. So first thing first, we are going to get the eigenvalues by solving this determinant. So if we solve the determinant of this equation, H naught minus lambda I, we are going to get the values for the eigenvalues. So I is our identity matrix, which is given as 1 0 0 0 1 0 and 0 0 1. So if we solve the determinant of this matrix, we are going to have this expression lambda cube minus 5 lambda squared plus 8 lambda minus 4 equals to 0. If we solve this equation, this cubic equation, we can use the try and error method. So we just try values that will give us 0. So we have these three values that solved the equation. So our eigenvalues are 1, 2 and 4. So we can get our eigenvector by defining a vector like this. So I'm calling it A1, E2, E3. So these are state vector. So these are eigenvectors. So our aim is to define the eigenstates of this vector. So let's move on. So I'm calling x bar, which I'll still change later to our psi, our Greek symbol, to be our eigenvector. So we're going to solve it for the three states. So when lambda is 1, if we substitute 1, then this expression here, this matrix, becomes this matrix. So if we solve this by matrix multiplication, we are going to have these expressions. So equation 1, E1 is equals to negative E2. And from equation 3, E2 is going to be equal to negative E3. So this expression for our eigenvector becomes this. It becomes given as this. So you see, it has become this. And by normalization condition, we have to normalize this by taking the square root to the sum of square of every term here. So if we do that, we're going to have E2 to be 1 over root 3, which we can substitute back to get our three vectors. So these are three eigenvectors. So this is the first state, this is the second state, and this is the third state. Mind you, I only solved for this, so it is your duty to perform the same matrix multiplication, a similar approach to solve for this, and also to solve for the third state. So our energy up to the second order is going to be given mathematically as this expression En0, En1 plus En2. So we have three states. So we are going to solve this energy for the three states. So first of all, for the three states, using this expression, the unperturbed energies becomes 1 to 4 respectively, which we can solve directly. Now let's go to first order correction energy. The first order correction energy is given by this expression. I know you are used to this expression. So you see, it is En1, where N is our state. So we don't know what the state is. My state 1, state 2, state 3. So we are going to be solving for the three states. So this is our formula. Don't forget that this expression is equal to this expression in quantum mechanics. So we can state 1, we are going to solve this matrix for state 1. So if we want to solve this matrix, we can start by breaking out this part from here. So if we break it out from here and we solve this matrix, and we can complete the solution to give us 0.0667. For state 2, we can do the same. We can solve this matrix by matrix multiplication. So we can bring in the two states and perform a matrix multiplication. We are going to have this expression, which is going to give us 0.15 for state 2. So if we do the same thing for state 3, we are going to have state 3 E3 to be 0.31667. So that's for state 3. So we can summarize here by saying E1, E2, and E3 is given by this expression. Now let's solve for the second order correction energy. Don't forget, our formula for our second order correction energy is given by this. So don't forget, this is very important. J is not equal to N. We have 3 states here, which is from the ground state, the first excited state, and the second excited state. So since we have 3 states here, we are going to substitute for n equals 1, n equals 2, and n equals 3. So starting from n equals 1, our first state should be given as this. Mind you, if n is 1, then j can only take value of 2 and 3. So if we expand this summation, we are going to have this expression for our state 1, E1 to order 2. So if we substitute the matrix, we can solve for this matrix again, and we can also solve for this matrix as well, and we can substitute back to get E1 to order 2 to be negative 2/675, and for state 2 we can do the same thing. So if we do the same thing, it means that n is 2. So when n is 2, it means j can only take values of look at it here, negative 1 and 3, not negative, please. You can only take value of 1 and 3 when n is 2. So if you substitute it again, we are going to have this expression. Then lastly, for state 3, we are going to have this. N is 3 and j can only take value of 1 and 2. Don't forget. So if we do that same expression by finding the matrix here, we are going to have this expression. So if we sum up to the second order, it's going to give for state 1, this is for this first state, this is for the second state. So let's call this first, this is for the second state, and this is for the third state. So you are going to observe that the final energy we are going to have is going to be close approximately to our unperturbed state, which is 1, 2, and 4. So you see, if you approximate this, it's going to give you 1. If you approximate this, it's going to give you 2. And if you approximate this, it's going to give you 4. Okay, see you in our next class. Have a great day.